Okay, so now what if we have more frogs? Again, let us remember our example of the lily pads and the frog. So we had one lily pad, 2 and 3. And right now, instead of bringing actually just one frog to this lily pad section, we're going to bring 100 frogs or 1,000 or how many you'd like. And we are actually wondering if we change our initial distribution, so how many frogs are on each lily pad, and we go over a cycle, so every frog takes a step, then the distribution does not change. So in mathematical terms, if we have a distribution and we multiply it with our transition matrix, we obtain our original distribution back again. This is called a stationary distribution or an equilibrium. So this is a stationary distribution. Like that. So we have an irreducible finite Markov chain. What irreducible means we'll get in the later section of definitions, but it is finite, and we know in that case that there is a unique stationary distribution. So what we're going to look for is such a distribution of pi for which this Markov chain does not change when it takes a step. So if we're going to write that down, we're going to have pi 1, pi 2, and pi 3 as our initial distribution multiplied with p, and our transition matrix, our p, was as following. It was a 0, 0.6, and 0.4. Then 1, 0, 0, 0.8, 0.2, and 0. So what we want is when this is multiplied, that this returns again pi 1, pi 2, and pi 3. Furthermore, what we also know is, of course, that pi 1 plus pi 2 plus pi 3 is 1. With this information, we can actually create or recreate our initial distribution. Let's do that. So if we multiply this initial distribution with our transitional matrix, we get the following. For pi 1, because this should be equal to, again, pi 1, pi 2, and pi 3. And when we multiply this vector with this matrix, we get a vector back. That means that for what will result in this position is equal to pi 1, which will be, of course, pi 1 multiplied with 0, and then you get pi 2 multiplied with 1, and pi 3 multiplied with this. Then again, these are all multiplied with each other and added. So for our first value, we see that we get 0 times pi 1, 1 times pi 2, and 0.8 for pi 3. So let's write that down. Pi 1 is equal to pi 2 plus 0.8 pi 3. For pi 2, we get 0.6 times pi 1. It's 0.2 for times 0, so there's no pi 2, plus 0.2 times pi 3. For pi 3, we only have one, namely 0.4 times pi 1. And then, of course, we also have pi 1 plus pi 2 plus pi 3 is 1. And these are 4 conditions that are important. So let's solve this. And we can solve this by working towards 1 pi value. And right now, let's work towards pi 1 because pi 3 is already written down in pi 1, which makes it way easier. So we only have to rewrite pi 2 actually. So we know that pi 3 is 0.4 pi 1. So let's fill that in our pi 2. So we get pi 2 is 0.6 pi 1 plus 0.2, open the bracket, and we fill in here 0.4 times pi 1. We just substitute in, which results in 0.6 pi 1 plus 0.08 pi 1, which is 0.68 pi 1. That's pi 1, yes. So now we have already a pi 1 here, which is nice. We have a pi 1 at pi 3, and we only have pi 1 or pi 2 in terms of pi 1 here. Now we can substitute everything in our third equation. So let's do that now. If we write down everything in our third equation, we get, let's write down over here, there's more room. We get pi 1, or way to the left here. We get pi 1 plus, now we replace it with what pi 2 was, which is in our case 0.68 pi 1. Like that, plus pi 3, and pi 3 we already knew was 0.4 pi 1, and this is equal to 1. Now we can add everything, so we get to 2.08 pi 1 is 1, and our answer, final answer, is pi 1 is equal to 0.48. Now we have this, which is very nice. Now we can substitute this into our other pi's. So we know pi 1. For pi 2, we knew it was 0.68 multiplied with pi 1. Well, we know pi 1 right now, which is 0.48. So this will result in the answer of pi 2 is equal to 0.33 approximately. And then the same for pi 3, which was also very easy from the beginning, which was 0.4 times pi 1. 0.4 times pi 1, which is 0.48. Together, this is equal to 0.19 approximately. Now if we can see that if we add this value, this value all together, we get 1, which is nice. And this concludes our stationary distribution that we have found. We have found a stationary distribution for the following values. Our stationary distribution, pi, is equal to 0.48, 0.33, and 0.19, or approximately. So if we have 100 frogs, if we put 48% of those frogs on lily pad 1, 33% on lily pad 2, and 19% on lily pad 3, then after one transition, we would still have the same number of frogs on every lily pad. Even better, after each transition, we have the same frogs on each lily pad, approximately. So this is what stationary distributions are and how to calculate them. It is just an initial distribution, and with your Markov chain, every transition or every step that you take does not change the distribution over the Markov chain. Now let's head into definitions, because Markov chains have a lot of names attached to them, and I will briefly tell them and elaborate a little bit on them. So first we have a state space S, which is called S, which is our state space. This is a set of states of our Markov process. As many states as you like. Could even be 1, could even be 0, then you would not have a Markov process. Then you have our initial distribution. Let's make an S sign of this. We have initial distribution, which is also called pi, or denoted as pi, which is this. This is just how the Markov process is initialized, what values go where. So yeah, it is just the initialization. Nothing more really can be said about that. It is how many percent of, or how many frogs in our case, go to which lily pad. Then we have a transition matrix, which we already have seen so far, which is denoted by P, and it saves all the transitions, so going from one state to another, from states to all other states. And we have seen them many times as well. Then we say that B is reachable from A if we can get from state A to state B, which we denote with A with an arrow to B. If B is also possible to get from A, so A is reachable from B, then we denote that with an arrow from B to A, and together you can write this as this, which is also called a communicating states, And you can also have a clause. A clause is just a set of states with something special about them, some property. With a property. For example, you can have a communicating clause, which means that every state in that set communicates with each other, can communicate with each other. Well, since we have a communicating clause or communicating states, we also can have a closed clause, which means that once you enter states in this clause, you cannot leave these states. It is impossible to leave. So you can only transition to states that are within this clause. For example, let's make a quick example here to the left. If you have a Markov chain, 1, 2, 3, 4, like this, once you enter state 2 or 4, there's no leaving state 2 or 4 because you can't go back to 1 or 3. You stay in state 2 and 4. So that means that state 2 and 4 are your closed class. Good. Now we of course also have an absorbing state, which is actually a closed class with only one state in it, or a state which you cannot leave. So once entered, so absorbing state, impossible to leave. Then, as I mentioned before in the video, we have an irreducible Markov chain, which just says that our state space our state space S is the communicating class. So every state is reachable from every other state. The class that we had here, this Markov chain, was not irreducible because there was a closed class in it. Not every state was in the communicating class. If you are in one state, you need to be able to visit every other state, even itself. Then your Markov chain is irreducible. It's never that once you leave this state, you're never able to return. Which is actually our next thing. We have recurrent states, a recurrent state, and a transient state. A recurrent state means that once we are in a specific state, as I, at x0, the probability that we will return to this state eventually is 1. If t is large enough, so t can be almost infinity, it is possible to return to the state, and then that state is called recurrent. However, on the other side, if the probability of returning to a state once entered is 0, then it's called transient. And our last definition is called a regular Markov process, or Markov chain. Markov chain. And what that says is that we have our transition matrix P, and in every of our entries in our matrix, none of them is 0. So none of the entries in P is 0. If that is the case, then of course we can also look at taking multiple steps. So let's say we have a Markov chain which contains some 0 elements in it, but if we take the power of it, so we call that if you have a transition matrix and you take the power of the matrix, you're actually looking not at one step but taking 2 steps in the Markov chain. What the probability is of reaching a state when you are taking 2 steps, or 3 steps, or 4 steps, depending on the power of the transition matrix. And if there is one matrix, if there is a power that you can take of the matrix where each element in the matrix is not 0, then you still have a regular Markov chain. So none of the entries in P is 0, or actually none of the entries in PT is 0 for t bigger than 0. And of course, the only whole numbers. And when there's such a specific t, for such specific t, t0, that is the lowest possible t for which this is true, then this is called a T, or in this case T0, regular Markov process, Markov chain, where T0 is a number. So for example, if you have a Markov chain which is regular with 5 steps, you can go from each state to any other state, even your own state, in 5 steps. Then it is called a 5 regular Markov chain. And these are one of the most important Markov chain properties or definitions used. Markov chains are very important in weather applications and even on your phone. So initial distributions are also a big part of those things. Those are the only things we have left for Markov chains. And after this, we will continue with the complex plane.